Hello, this video is one of the modules on offer as part of the Foundation online training course. Our unique course has helped over 10,000 people to study for their foundation exam, and the course consists of online lessons, videos like this one, quizzes and mock tests. To access our free course and to get the latest version of this video and our collection of videos, go to www.hamtrain.co.uk. Now, on with the module.
Hi, this is Kelly from Essex Ham and welcome to Foundation Online, getting you started with amateur radio. Here's what we'll be looking at in this module.
Hello, my name's Pete and I'll be your guide for this module.
Technical basics.
In this module, we'll look at the technical basics that you'll need for your foundation exam. When studying for your foundation exam, you'll need to understand the technical basics. And in this module, we look at units and symbols, voltage, current, resistance and circuits, conductors and insulators, the two formulas that you'll need to learn, frequency and wavelength, and digital signals. On the screen now are the units that you'll need to learn: voltage, current, resistance, power, frequency and wavelength. Let's look at each one individually. We start with voltage, which is also known as potential difference. The symbol for this is a capital V, and it's measured in volts, with a capital V for the units. Next up, current. The symbol for that is a capital I, and current is measured in amps, capital letter A. Next, resistance. The symbol for that is a capital R, and this is measured in ohms. And for units, we use the Greek symbol omega. Now we move to power. The symbol is a capital P, power is measured in watts, and the units are capital W. Now from the radio side of it, frequency. The symbol for that is a lowercase f, and frequency is measured in hertz, which actually means times per second. The units, capital H, small z. And the wavelength. The symbol for that is the Greek symbol lambda. Wavelength is measured in meters, and the units are small m. Now, large and small units. You're expected to know everything from micro, milli, kilo, mega and giga, and at any point in the exam you could find a reference to something like this. Let's start with the large ones first, because that's a little bit easier. So kilo should be fairly straightforward, 1000, lowercase k. Example there, 2000 ohms would be 2 kilo ohms, that's resistance. Mega is another straightforward one, 1 million, so 1 and 6 zeros, capital M. And the example here, 3 megahertz is 3 million hertz. And at the top end we have giga, which is 1000 million, or 9 zeros, symbol capital G. And Wi-Fi, your home Wi-Fi system, 2.4 gigahertz would be 2400 megahertz. That's the large ones. Now let's look at the small ones. We have milli, which is 1000th, 0.001. Little m as the prefix. For example, 1 millivolt would be 0.001 volts. And the smallest one we need to worry about is micro, which is 1 millionth. And on the screen you can see the decimal value, the prefix, and an example. So that's micro, milli, kilo, mega and giga. Now we're going to look at some electrical symbols. On the screen here you can see cell, which is next to battery. A battery is actually made up of multiple cells. You can see the battery symbol here shows the plus and the minus, and you can see this one happens to be made up of 2 cells. So cell and battery, slightly different things. Next we have the symbol for a lamp. Can be referred to as a bulb. The correct term through the exam is lamp. Then we have an LED, a light emitting diode. The symbol here for a microphone, not to be confused with the symbol for a speaker. For some of the block diagrams you'll see later, the symbol for the antenna and the symbol for an earth. This is the symbol for a resistor. And this is a straightforward switch. Underneath are the letters SPST, single pole, single throw. This means it's a very basic type of switch. Single pole, meaning it's for one circuit, and a single throw, meaning it's only got the on or the off state. So it's just a basic on-off switch. And finally, a fuse, which you should be familiar with from mains plugs. Let's move on to talk now about current. Current is the flow of electrons in an electric circuit. You can see there the electrons moving in a single direction. The current is measured in amps, and the thicker the cable, the more electrons will flow, so a thicker cable can handle a higher current. Let's look at conductors and insulators. A conductor allows electrons to flow, whereas an insulator does not. Good examples of conductors: copper, brass, silver, gold and carbon. You should note that water is actually a conductor and current can flow across wet insulators. Looking at insulators: plastics, wood, rubber, glass and ceramics. So just be a little bit wary of water. Water on wood could still carry a current. Let's look now at batteries. As I mentioned earlier, a battery is a combination of cells, usually in series, so connected together as you see. A battery provides electrical energy from stored chemical energy and has a potential difference, which is measured in volts, across its terminals. Looking at a simple battery here, this would be an AA battery. It's called a primary battery, which means it's not rechargeable. Once you've finished it and the battery is expired, it must be properly disposed of. A secondary battery is rechargeable. It has a reversible chemical process. A car battery being a good example. A look next at polarity. A battery has a polarity, normally indicated by a plus and a minus, or red and black. And a battery must be connected round the right way. Some components, such as a simple filament lamp, have no plus and minus, and can be connected into a circuit either way around. Here's a quick demonstration that a filament lamp can be connected in either polarity. The polarity for many other components is critical, however, and they must be connected the right way round to ensure that they work. If you connect something round the wrong way, it could cause damage either to the components or to the equipment. We move on to circuits now. We're looking at a very basic electrical circuit. Here you see a battery made up of two cells, with the current flowing through a lamp back to the battery. So this would make the lamp light. A circuit is needed to allow the current to flow. And a circuit includes a source of electrical energy, such as a battery. Here we're looking at direct current, where you see the current flows from the plus of the battery, through the circuit, into the lamp, and then back to the battery. This circuit is providing DC, direct current. The current flows in one direction, from the battery to light the lamp. And remember, as I mentioned earlier, voltage is sometimes referred to as potential difference. We look now at alternating current, or AC. The direction of the current constantly changes between positive and negative. Positive, negative, positive, negative, over time. In the UK, the mains voltage is 230 volts, and it operates on a system of alternating current every 50 Hz. 50 times a second, it will alternate between plus and minus. Some of the basics there of the circuits, symbols and units. Let's look now at formulas. This is the formula for power. Power is measured in watts, and the power equals the voltage times the current. This is something that you'll need to know for your foundation exam. The formula won't be given to you in the exam, so you will need to remember it and understand it. One of the easiest ways of doing this is with the aid of the triangle that you can see on the screen now. So we have power, voltage and current, PVI. If you can remember that for your exam, that's a good start. In the exam, they're likely to give you two values and you're expected to calculate the third. Here in the triangle, you can see the P is over the V and over the I. So power is the voltage times the current. Power at the top, voltage times the current. Imagine a time symbol there. If you were after the voltage, that would be the voltage there is the power over the current. And if you were asked to calculate the current, I equals P over V, I equals P over V. So remember this triangle, and the trick is cover up with your thumb the one that you're after calculating. If you wanted V, thumb over the V, and it would leave you with P, the power, over the current. Let's look at an actual example of that. So let's take a 60 watt speaker, which is running from a 12 volt battery. What is the current? We have the power, we have the voltage, and we want the current. So we put our thumb over the current, the I, and that would give you P over V. So let's look at that example. Cover the I, and you get I is P divided by V. That would mean that the current is 60 watts, being the power, divided by 12 volts. So the answer, a nice simple 5 amps. We're going to now look at something called resistance, which we mentioned right at the start. In this circuit, you can see a battery, current flowing through a resistor, into the lamp, back to the battery. Pictured here is a basic resistor. So a resistor opposes or limits the flow of current. You can kind of think of it like putting your foot on a hose pipe. Less gets through the circuit. As I mentioned earlier, resistance is measured in ohms. And in this circuit, a resistor, which we're calling R, would cause the lamp to either be dimmer or to not light at all, depending on the value of the resistor. And when a resistor is used in a circuit, the resistor will get slightly hot. That's converting the electrical energy to heat the resistor. Which takes us to our second formula. This is called Ohm's Law. It's a very famous law. And voltage equals the current times the resistance. Again, nice easy way of remembering this is our triangle. V, I, R. So you could see the voltage equals the current times the resistance. The current equals the voltage over the resistance. And the resistance equals the voltage over the current. Exactly the same as we've learnt before. Let's look at an example. Let's say a piece of amateur radio equipment has a resistance of 24 ohms and needs a current of 0.5 amps. What is the voltage? So here we know the current and the resistance. So the current, 0.5 of an amp, times the resistance, 24 ohms. So the voltage is the current of half an amp times the resistance, 24 ohms. So 24 times a half, 12 volts. If either formula gives you any struggle, we do have a separate revision video that goes into that in a little bit more detail. But that's largely it, and in the exam you are allowed a calculator if you aren't 100% with maths. We're now going to move on briefly to a topic called series and parallel circuits. Apologies in advance, if electronics isn't your thing, this might be a little bit daunting, but do please bear with it, hopefully it'll make sense, and we do give some examples. So we're going to start off with an in-series circuit. And here the current will flow from the battery through the first lamp, into the second lamp, and back into the battery. The current that's passing through both lamps is the same. There's only one path from the positive to the negative, so the current is equal across both. The voltage is split between the two items though. So for argument's sake, if this was a 3-volt battery, 1.5 volts would be measured across here, 1.5 across here, giving you the total of 3 through the circuit. Again, examples to follow. The alternative to an in-series circuit is what's called in parallel. And what you can see here is the current leaves the battery and it now has 2 paths back to the battery, either through the first lamp or through the second lamp. 2 paths, and these 2 are in parallel. Here, the same voltage would be measured across both lamps. So the voltage measured across there is the same as the voltage measured across there. However, the current is split. So half of the current goes that way, half of the current goes that way. So you should see the difference. Here, the voltage is half and the current is the same. But here, the voltage is the same and the current is halved. Let's look at that as an example now. So let's assume that each lamp is the same and each lamp needs 3 volts to light up. So in series, you'd need 3 volts here and 3 volts here, meaning you need a 6-volt battery. If this lamp here blew, the circuit would break because you no longer get a full path back to the battery. Now if you look at that in a parallel circuit, because the voltage is equal across both of these, you'd only need 3 volts. If that needs 3 and that needs 3, in this configuration, they would both still get the 3 volts. However, the current is halved. Half of the current that way and half that way. This is because there are 2 paths. So you need to understand the difference. In a series circuit, half the voltage here, half the voltage there. In a parallel circuit, all of the voltage here, all of the voltage there. So you should see the relationship between the current and the voltage is linked. Now this in parallel bit can be a little bit tricky, so we'll look at it in a slightly different way, which might make it a little bit easier. So here's the drawing we've just looked at of a parallel circuit. Half the current that way, half the current that way. Sometimes it helps to think about current as water. So if we have current flowing through 2 equal paths, maybe 2 pipes, something like that, half of it will go down one pipe, half will go down the other. We could look at the same circuit in a different way. Exactly the same circuit, just drawn a slightly different way. So let's say this circuit is 4 amps. As the current leaves, it splits into 2. 2 amps goes that way, 2 amps goes that way, and back at this point it's back to 4 amps again. Exactly the same, just being split in 2 places. If you think about it as water coming down a pipe, half goes that way, half goes that way. And of course, if this lamp was to fail, then suddenly there's only one path and all of the current would go through the remaining lamp. Hopefully that makes sense. If not, watch it again and hopefully you'll get it. We're about 2/3 of the way through this module now and we're going to look at digital signals. A little bit of a gear change, please bear with me. In upcoming modules we'll talk about signals and some waveforms, but what you can see on the screen here is a representation of a piece of audio. You can see these signals are going up and down, they're changing in height and frequency. We'll look at this in more detail in a later slide. This is what an analog signal looks like, varying in height and frequency of the waveform. Digital signals are a stream of finite values, noughts and ones, taken at specific sampling intervals. So you can see analog and digital, very different. You'll be familiar with the idea of digital being noughts and ones. Digital signals are better at overcoming noise because they're either on or they're off. And for digital signals, you'll need some kind of computer processor and some software. So we've seen the difference between the analog and the digital signals, and there is something called an analog to digital conversion process. Digital signals are processed using a computing device of some kind. An analog signal, pictured here, can be converted to a digital signal using something called an ADC, an analog to digital converter. And you can go the other way, digital to analog, DAC. So digital signal here, you can see the noughts and ones, converted to an analog signal. Fortunately, that's all you need to know about signals at this point. Now we'll talk about frequency and wavelength. What you're seeing on the screen here is a sine wave. This is a signal which can be generated by an oscillator. There are two types of frequency that we care about at Foundation. There's RF, which is a radio frequency, and AF, which is an audio frequency. So that's something you could hear. And what you see here is the frequency to wavelength conversion table. You do get this in the exam. What you may be asked to do is work out the frequency from a wavelength or the wavelength from a frequency. What you can see here is we're looking at a wavelength of 20 meters. So 20 meter wavelength, that's quite long, about the length of about 5 cars. 20 meters, if you follow along on the chart with your finger to where the diagonal line intersects and then drop down, you would see that would give you a frequency of, looks like about 15 on here, it's actually 14. So 14 megahertz would be a wavelength of 20 meters. What you'll also notice, very important radio concept here, is as the frequency increases, you can see our frequency increasing here, the wavelength decreases. Again, you'll be given this chart in the exam, the frequency and wavelength lookup table. Let's take a quick look at individual frequencies. You could be asked any of these in your exam. The mains frequency is 50 Hz, so the alternating current changes 50 times a second. We now need to look at the audio frequencies, AF. The human hearing range on an adult with healthy ears would be somewhere between 20 Hz to 15,000 Hz, or 15 kilohertz. That's the range that a human with good hearing could hear. Audio communication, so to hear speech, would fit in a range between 300 Hz and 3 kilohertz. And we look now at the radio frequencies. As far as this exam is concerned, the range of radio frequencies is from 30 kilohertz, so you can see that's a lot higher than our human hearing, to beyond 3000 megahertz. At Foundation, we're concerned with 3 bands called HF, high frequency, VHF, very high frequency, and UHF, ultra high frequency. The HF band is 3 megahertz to 30 megahertz. VHF, 30 to 300, and UHF, 300 to 3000 megahertz. Don't worry too much about these numbers at the moment. We will come back to them, especially the radio frequency numbers, but these are all numbers that you'll need to learn for your Foundation exam. You'll be pleased to know that's it for the Technical Basics module. We've looked at units and symbols, where you need to remember the units and the prefixes. Some examples on the screen there. You'll need to be able to recognise these symbols: resistor, cell, speaker and microphone, etc. The basics of electronics, alternating versus direct current, and series and parallel circuits. The two formulas that you'll need, the power formula, PVI, and Ohm's Law, VIR, and do practice with those triangles. We've looked at digital signals, converting between digital and analog, and frequency versus wavelength. As the frequency goes up, the length of the wave reduces. And remember that lookup table that you're given in the exam. Thanks for watching this latest module of our Foundation online course. We hope you found it useful. If you're looking for some more help with your studies, we do recommend the Foundation Study Guide, available from Amazon in Kindle or paperback format. Thanks for watching again, and best of luck with your studies. As a reminder, this video is part of the free Foundation online course. If you're studying for Foundation, sign up and get access to all of the course material, including slides, lessons, handouts, videos, quizzes, and our mocks. You can sign up at www.hamtrain.co.uk.